In this video, we solve problems 1, 2, and 3 from the Differential Equations quiz number 6 from the spring 2021 semester. These first three problems all relate to the standard L24 in our standards-based grading course, which is about the definition of the Laplace transform. So in the first problem, we're given a piecewise function, and we're asked to use the definition to find the Laplace transformation of the function. And then the next two problems involve using our table of Laplace transforms to compute Laplace transforms of functions as well as inverse transforms of functions. And we'll have to use some partial fraction decomposition as well with the inverse transform. So let's solve this first problem first. It says this. It says given the piecewise function f of t equals e to the negative 3t on the interval from 0 to 5 and 2t minus 6 on the interval from 5 to infinity, use the Laplace or the definition of the Laplace transformation, and that's really important. We want to use the definition to find f of s. We do not want to use the Heaviside function, and I told my students I want to see evidence that you know the definition and how it applies, and I asked them to be sure to state any conditions on s necessary for the improper integral to converge. So I would start by stating the definition of the Laplace transformation. So we have the Laplace transformation of f of t equals the integral from 0 to infinity of e to the negative st times f of t. Now this is optional, but I prefer to graph this function as well. So you don't have to do this, but if we graph f of t, it can help us visualize what it is we're doing. F of t is e to the negative 3t on the interval from 0 to 5. So when t equals 0, we're going to have e to the 0 there, so that's 1. And when t equals 5, we'll have e to the negative 15th, which is very small. So it's an exponential function. It's decaying. It's going to go like this. This is not to scale, but it's just giving us a rough sketch of what's going on. So we're going to have something that looks roughly like that. Now, we're also told that on the interval from 5 to infinity, oops, and there would be an open circle there because 5 is not included on that, or 5 is not included on the interval where this f of t is equal to this e to the negative 3t. Okay, so on the interval from 5 to infinity, including 5, what we would have here is it's a linear function, and when t equals 5, we would have 10 minus 6, which is 4. And then it has a slope of 2, so we're going to go up 2 and over 1 to get another point. So if this is 4, this would be 6 when t is equal to 6 here. So this is our f of t. Now, because it's defined in two pieces, we need to evaluate this integral from 0 to infinity by splitting it into two pieces. First, we'll evaluate the integral from 0 to 5. That's t equals 0 to t equals 5. And then we'll evaluate the integral from 5 to infinity. So this is the same as this times f of t on that interval plus this times f of t on that interval. On the interval from 0 to 5, f of t is e to the negative 3t, excuse me. And on the interval from 5 to infinity, f of t is 2t minus 6. So when we use the definition, those are the two integrals that we're going to evaluate. Let's write that down. We'll write the Laplace transform as the sum of two integrals, and then we'll evaluate those integrals. And this is by definition f of s. So we have f of s equals the integral from 0 to 5 of this exponential times that exponential. Now remember our exponent properties. If we have x to some power times x to a different power, we add the exponents. That works for power functions, but it also works for any kind of exponential function. If the base is the same, you get to do that. Sorry to focus my camera. So if I have these two exponentials, I can add the exponents. And I think I'll factor out the -1 as well and factor out the t. So I end up with s plus 3 times t times -1 as my exponent. And the other piece I'm not going to worry about for right now. That's the integral from 5 to infinity of this. I'll take the polynomial and put it out front because that's how I traditionally like to write my integrals. If I've got an exponential and a polynomial, I like to write the polynomial first. Okay, so we are here now. Let's evaluate this first piece first. Now, in Calculus 2, or probably in Calculus 1, you learned that the antiderivative of e to the kx is e to the kx times 1 over k plus c. Now remember where that comes from. The derivative of e to the kx, where k is a constant, is e to the kx times the derivative of the inside. So we would multiply by k if we were taking the derivative. Since we're taking the antiderivative, rather than multiplying by k, we're going to divide by k. So that is what I'm using here, where this is my k. K is the -1 times that quantity s plus 3. So what we'll have here is e to the exact same power divided by the k, which is the negative quantity s plus 3. And we'll evaluate this from t equals 0 to t equals 5. At t equals 5, we have this e to the negative s plus 3 times 5 over negative s, or negative quantity s plus 3. And when t equals 0, we'll have an e to the 0 in the numerator, so that's just a 1. So we'll be subtracting something negative, so that means we're going to add 1 over s plus 3. So that's that piece. If you want, you could distribute the 5 and the -1. It's not necessary, but you can do that if you want to. You can pull the negative out front. There are lots of different ways to write that correctly. Now, when it comes to the improper integral, you've got 3 things that you always have to do. For the improper integral, remember, we always want to write it as a limit. Improper integrals are actually limits. So first, we write the integral as the limit of a proper integral. Because right now, the domain is unbounded. T is just going off to infinity. And instead of doing that, we want to bound that domain. We want to evaluate the integral from 5 to b. That's giving us a certain area under the curve, or the curve given by 2t minus 6 times e to the negative st, where s is just a parameter. And that's going to give us a specific area in terms of b. And then we want to say to ourselves, okay, well, what happens to that area as b goes to infinity? So after writing the integral, the improper integral as the limit of a proper integral, we need to evaluate the proper integral using the fundamental theorem of calculus. So we have the limit as b goes to infinity. I'm ignoring that for right now, of this. And for this piece, I would recommend using tabular integration by parts. Anytime I have a u as a polynomial and dv as either an exponential, a sine function, or a cosine function. I like to use tabular. It's really nice and easy and very straightforward. So this is the integral of u times dv. So u is my polynomial, dv is everything else. When we use tabular, we usually ignore the dt. And when we're using tabular integration, we differentiate in this column until we get 0. So the derivative of that is 2, the derivative of 2 is 0. Now in this column, we anti-differentiate until we have the same number of rows in both columns. So I'll take the antiderivative of this using my e to the kx rule again. So the k is that negative s. So we're going to divide by s or multiply by negative 1 over s, same thing, every time we take an antiderivative. So we'll have that right there. And then because of the integration by parts formula, which comes from the product rule, we have this sign convention on the left. And it's really not a convention, it's necessary in order for these the integral of u dv to equal the result that we're about to come up with. Okay, so the antiderivative of this is this times positive 1 plus this times negative 1 plus c. So we have negative 1 over s times 2s or 2t minus 6 times that exponential. And then we're subtracting 2 over s times, or 2 over s squared times that exponential. And we evaluate all of that as b goes from, or as t goes from 5 to b. I kind of ran out of space there. Sorry about that. Okay, so I think over here I will distribute that 5. So I have e to the negative 5s minus 15. Got an s plus 3 in the denominator. I'm adding 1 over s plus 3 here. And over here, I need to substitute b, substitute in 5, and subtract. So I'm just going to write that whole thing on this next line. When I substitute b, let's see, let's actually factor out the exponential. This is what I get. I get 2b minus 6 over s minus 2 over s squared. And all of that is multiplied by e to the negative s times b. And then when I evaluate this at t equals 5, and we want to subtract that, we'll have 2 times 5 is 10, 10 minus 6 is 4, so we'll have negative 4 over s times e, well, let's factor out the exponential there as well, times e to the negative 5s minus 2 over s squared times e to the negative 5s. Oops, sorry, I'm off the screen there. And then we want to take the limit of this result as b goes to infinity. Well, as b goes to infinity, if s is positive, this goes to 0 and this goes to negative infinity. So we have a negative infinity times 0 indeterminate form. And that means we need to rewrite it and then perhaps use L'Hopital's rule after our rewriting it as infinity over infinity or 0 over 0. Now there are no b's here, so that's just going to come down. That's going to be treated as a constant after we distribute that negative. Okay, so let's apply L'Hopital's rule, or let's rewrite this first and then apply L'Hopital's rule to that. So we've got this plus this plus this. Plus the limit as b goes to infinity of this expression. If I want to write this as a negative infinity over infinity indeterminate form, I'll just put this in the denominator. Now these limits are just like this. This is for s greater than 0. If s is greater than 0, this is e to a large negative power, large in magnitude, but negative. And that's when that would go to 0. If s was negative, well, then we would have a negative times a negative, which would be a positive, and then this would go to infinity. So if s was negative, this would go to infinity, and then this would go to infinity. And so we would end up with an infinity times infinity, which would clearly be infinity. So in order for this to possibly converge to anything, we need to force this restriction. We need to say, well, if S is positive, we can keep going. So we're going to force S to be positive, and then we'll keep going. Okay, so I want to put my exponential in the denominator. And I still have this negative 1 over S times 2b minus 6 minus 2 over S squared in the numerator. And now as b goes to infinity, this is an infinity or negative infinity over infinity indeterminate form, provided that S is positive. Okay, so we can use L'Hopital's rule on that one. So I'm just writing everything else over again. Not really doing anything to it. I'm just rewriting it. And then this limit by L'Hopital's rule is equal to the limit as b goes to infinity of the derivative of the numerator with respect to b, which is going to give me a negative, or excuse me, a 2 from this, and then that would be 0, and that would be 0. So we'll have a 2 times the negative 1 over s. That's going to be negative 2 over s over the derivative of this piece with respect to b. Derivative of an exponential is the exponential times the derivative of the inside with respect to b. We're treating the s as a parameter or a constant in this case. The derivative of a constant times our variable is just the constant. So right now we've got a constant over a constant times e to the sb, where we're assuming s is positive. If s is positive, s times b is positive as b goes to infinity. And so as b goes to infinity, this is going to go to infinity. So we have a constant over something very large. A constant over something very large is something very small. So this will go to 0, provided that s is positive. That restriction that we made earlier is important. Should still be there. So this is our Laplace transformation of f of t. So we'll call that f of s. And that will work as long as s is positive. Otherwise, f of s does not exist. Okay, so that is the definition. What did we do? We evaluated, first we wrote this as two integrals. We evaluated the first integral just using the fundamental theorem of calculus. It's pretty straightforward. You just treat s as a constant. Then this piece you have to write as an, or it is an improper integral. So you have to write the improper integral as the limit of a proper integral, evaluate the proper integral using the fundamental theorem of calculus. It happened to require integration by parts for the antiderivative. And then after we did that, that gave us this result. When we plugged in b and 5 and subtracted, that's the result of the fundamental theorem applied to this integral. Then we say, okay, we'll evaluate the limit. What is the limit of that? And the limit of this piece turns out to be 0. But to prove that it's 0, we say, well, this is a negative infinity times 0 indeterminate form, so let's write it as a quotient so we can apply L'Hopital's rule, and we did. Okay. All right, so that was the first question. Let's look at the second question. So here's our second question. It asks us to use the table of Laplace transforms to find the Laplace transform of each of the given functions, and in part A, we're given this function. So we've got a constant times t to some power here and here. So we're going to apply the appropriate transform for that. We have a constant here and a hyperbolic sine function and a hyperbolic cosine function. So I go to my table. This is the table that is provided to you or was provided to you during your quiz. And we have found the appropriate entries in the table. And remember, the Laplace transformation is a linear operator. So you can sort of ignore any constant multiples of functions, and a constant like this, we can think of that as just a multiple of 1. So these are constants times t to some power. Well, entry number 3 in our table is appropriate for that, because it says if f of t is t to the n, the Laplace transform is n factorial over s to the n plus 1. Okay, so I wrote that down, and I've got a constant here. So I will use the Laplace transform of 1 for that, because that's just -6 times 1. The Laplace transform of 1 is 1 over s. That's entry number 1 in our table. Then I have the hyperbolic sine and hyperbolic cosine functions. So I'm scrolling. There I am at number 12 and number 13. Entry number 12 tells us that the Laplace transform of hyperbolic sine of kt is k over s squared minus k squared. And the Laplace transform of hyperbolic cosine of kt is s over s squared minus k squared. So we're just going to use these entries here. It's a 13, not a 3. And the fact that the Laplace transformation is a linear operator. So the Laplace transform of f is this. First we bring down the 5, and then we multiply by the Laplace transform of t to the 4th. So I'm pattern matching this t to the 4th with this t to the n. I'm just identifying n is equal to 4. And then according to this entry, we'll have 4 factorial divided by s to the 4 plus 1, or s to the 5th. Here we'll bring the -7 down, and we'll use the same rule, but this time our exponent is 3. So we take the Laplace transform of t to the 3rd. Since n is 3, we'll have 3 factorial over s to the 3 plus 1, or s to the 4th. Then we bring the -6 down, and we multiply by the Laplace transform of 1, which is just 1 over s. On this one, we bring the 2 down, and pattern matching again, this is hyperbolic sine of 3t, and we have a rule for hyperbolic sine of kt. So k for this one is 3. According to our rule, the Laplace transform of that is k, which is 3, over s squared minus 3 squared, or s squared minus 9. On this one, we bring the 3 down. I'm going to do something similar. It's hyperbolic cosine of kt. K is 2. With hyperbolic cosine, it looks just like the hyperbolic sine, except you have an s in the numerator. So we'll have s over s squared minus k squared. If k is 2, k squared is 4. So that is our answer. It's just not simplified. Looks like we've got 4 factorial times 5. 4 factorial is 2 times 3, which is 6. 6 times 4, that's 2 times 3 times 4, which is going to give me 6 times 4, which is 24. And then we take 24 and we multiply by 5. So that's going to be, 20 times 5 is 100, and 4 times 5 is 20. So it's going to be 120 over s to the 5th. Here we've got 3 factorial, which is 3 times 2 times 1, or 6, times the -7, which is -42. And of course, that's just going to give me a 6 over 1 times 1 over s is just -6 over s. And I'll multiply this fraction by 2 over 1, and I'll multiply this fraction by 3 over 1, and we'll have 6 over s squared minus 9 here, and 3s over s squared minus 4. So that is our answer for part A. Part B is very similar, but I think it involves different functions. So in part B, you're given g of t, and you're told that that equals 10 times e to the -4t plus 8 times cosine of 5t minus 3 times sine of 2t. So I would go to my table of Laplace transforms, And I'm looking for e to the at, which is actually right there, entry number 11. The Laplace transform of e to the at is 1 over s minus a. And I've got a cosine function and a sine function. Oops, there we go. So those are entries 7 and 8. The Laplace transform of sine of kt is k over s squared plus k squared. And the Laplace transform of cosine of kt, that's number 8, is s over s squared plus k squared. Okay, so these are the entries that we'll use. And again, we'll use the fact that the Laplace transformation is a linear operator. So the Laplace transformation of g of t can be found this way. Oops, I'm using blue instead of black. That was not my intention. First, we bring down the 10, and then we're pattern matching. I have the e to the negative 4t. That looks like e to the at, where a is the number multiplying our t, so a is negative 4. So we take the Laplace transform of e to the negative 4t just by matching that pattern. It's 1 over s minus a, so we're subtracting negative 4, which is the same as adding 4. Here we bring the 8 down, and we take the Laplace transform of cosine of 5t. Well, that matches this pattern, cosine of kt, where k is equal to 5. So according to this rule, we have an s over s squared plus k squared. If k is 5, k squared is 25. Over here, we'll bring the negative 3 down. Pattern matching again. This is sine of 2t. And we've got a rule for sine of kt. So we identify k. K is the number multiplying t. In this case, that's 2. So we will have k, according to this rule, which is 2, over s squared plus k squared. 2 squared is 4. And if you want, you could write this as itself over 1, that as itself over 1, and that as itself over 1. So when you multiply straight across, this is what you get. You get 10 over s plus 4 plus 8s over s squared plus 25 minus 6 over s squared plus 4. And that is that piece. Now that is the end of problem number 2. Now let's look at problem number 3. Okay, so this is problem number 3. It says use the table of Laplace transforms and partial fraction decomposition to find the inverse Laplace transform of the function. So clearly we've got a cubic polynomial in the denominator, a quadratic polynomial in the numerator, and that means that we don't have an entry in our table that looks anything like that. I'm not going to go through the table with you right now, but if you do look through that table, you'll see that there's nothing that matches this pattern. But if I use partial fraction decomposition to rewrite this, I will be able to take the inverse transform of each term. So the key is to write this as the appropriate partial fraction decomposition of this expression, and then just take the inverse transform piece by piece. So we'll first state, or first we'll factor the denominator as much as possible. And then once we factor that denominator as much as possible, we'll state the appropriate partial fraction decomposition for the particular function that we're looking at, f of s. So I look at these 3 terms and I see that they all have an s in common, so I'll factor that out. S times s squared gives me s cubed. S times a negative 2s would give me s squared, because I need one more s to have 2 s's. And then s times negative 3 gives me the negative 3s. Now for this one, I might ask myself, okay, do I have 2 numbers that multiply to give me negative 3 that add to give me negative 2? And I do. S minus 3 times s plus 1 will work, because negative 3 times positive 1 is negative 3, and negative 3 plus 1 is negative 2. So that is my factored denominator. So f of s is really this. Oops. And that means I've got 3 linear factors. None of my linear factors are repeated. So it's just going to be a pretty straightforward partial fraction decomposition. It's going to be a constant over the first factor plus a constant over the second factor plus a constant over the third factor, where those constants are to be determined by us. Now, in order to find the values of those constants, we'll multiply both sides of this equation, just thinking of this as the equation, so leaving off that label f of s, by the original denominator. So you do s times s minus 3 times s plus 1. Okay, and then reduce factors wherever you can. Well, that's for the partial fraction decomposition. That's in order for that to be equal, I'd have to multiply f of s by that as well. So I don't want that there. I don't want that equality. These are equal now. Okay, so the s's will reduce, the s minus 3's will reduce, and the s plus 1's reduce there. The s's reduce here, the s minus 3's reduce there, and the s plus 1's reduce there. And after simplification, what we have is the original numerator equals a times the quantities s minus 3 and s plus 1. And then we have b times s times the quantity s plus 1. And then we have c times s minus 3. Now, in order to find the values of a, b, and c, we just choose values of s that will cause each of these factors to be 0. So this factor is 0 when s is equal to 3. So I substitute s equals 3 on both sides of the equation. So I'll have 2 times 3 squared plus 3 times 3 minus 3 equals what I get over here when s is equal to 3. When s is equal to 3, this 3 minus 3 is 0, so this piece is gone. It's all zeroed out. And when s is equal to 3, this piece is gone. So the only piece that's not 0 is this piece. So we'll have b times s, which is b times 3, times 3 plus 1, which is 4. So we'll do a little bit of arithmetic. This is 9 times 2, which is 18. And that's another 9. So we have 18 plus 9 is 27. And 27 minus 3 is 24. And that's equal to 12b. So b is 24 divided by 12, or 2. Okay, now pick a different value of s that makes one of these factors 0. So I'll choose s equals -1 this time. So I'll have 2 times -1 squared plus 3 times -1 minus 3. -1 squared is just +1. So it's going to be 2 times 1 minus 3 minus 3. And on the right-hand side, when s is equal to -1, s plus 1 is 0. So this is 0 and this is 0. The only part that's not 0 is this part. So let's just evaluate this expression at s equals -1. So you have -1 times c times -1 minus 3, which is -4. -1 times -4 is +4c. This is 2 minus 6. 2 minus 6 is -4. So c is -4 divided by 4, which is -1. Okay, now we just need to find one more value of s. We already forced this one to be 0 by letting s equal 3. This one was 0 and s equals -1. And now we want s to be 0 because the factor s by itself would be 0 when s is 0, clearly. So when s is 0 on this side, we have 2 times 0 squared plus 3 times 0. So that's all going to be 0 minus 3 equals something plus something times 0 plus something else times 0. So this is 0 and this is 0. The only part that's not 0 is this. So we have a times -3 times 1. So that's -3a equals -3. So a is equal to 1, or -3 divided by -3. So our f of s, which was this, can be rewritten in this way. A is 1, B is 2, and C is -1. And if you want to, you can even go further. You can factor out that 2. Okay, so now we want to compute the inverse Laplace transform of this. And the inverse Laplace transform is an integral operator. And we're just taking the inverse transform of this piece and this piece and this piece. And those require entries from our table that we've used before. We had that the Laplace transform of 1 was 1 over s. So the inverse Laplace transform of 1 over s is equal to 1. So when we're looking at our table, we've got an f of t column and an f of s column. So rather than going from right to left, we're going from left to right, basically. Or if you want, you can write it from right to left. You can write it in the reverse order. So the inverse transform of 1 over s is 1, and these look like 1 over s minus a. The inverse transform of 1 over s minus a is e to the at. Those were from entries number 1 and number 11, but I've written them backwards. So we take the inverse transform of 1 over s, that gives us a 1. Then we bring the 2 down. This is 2 times 1 over s minus a. Pattern matching, our a is equal to 3 there. So this would be e to the at. So that'll be e to the 3t. And then we're subtracting 1 over s minus a. If negative a is positive 1, that means a is -1. This is e to the at, where a is -1. So we've got -1 times t. So that is our f of t. And that is the end of our video covering that first course standard, standard F20 or L24, which is about the Laplace transformation defined. Now, this is one version of the quiz. There were multiple versions of the quiz, so you may not have seen these questions, but you probably saw similar questions. Those videos will be posted later today as well.